everyone. Welcome to Subnetting a Little Bit. This session will explain a method of analyzing an IPv4 host address. Consider it a crash course. Listed here are some of the topics we will discuss. Today we will present a lot of very useful information, so you'll want to pay close attention. Here is a partial list of the information we will gather from the analysis of a host address. Before proceeding, you need to understand how to determine and analyze the subnet address map. If necessary, watch the videos referenced in the description box below. Understanding the subnet address map is important because it allows you to extract a lot of information about an address, including the items shown here. So let's get started. We can use the subnet address map, or simply address map, to extract the total number of subnets possible. The formula for total subnets is 2 to the s, where s is the number of subnet bits in the subnet address map. Subnet bits are represented using the letter S in the address map. Let's look at the first entry. Keep in mind that an IPv4 address is made up of 4 octets adding up to 32 bits. Uppercase letters in the address map represent 1 octet, or 8 bits. There are 4 subnet bits in the first address map. Applying the formula gives 2 raised to the 4th power. A subnetting scheme with this address map can provide a total of 16 subnets. In the third entry, ignore the bits denoted with a lowercase n for now. We use them when subnetting an address that has already been subnetted. Another video explains it in detail. For now, only consider the S bits. Since it has 6 subnet bits, a subnetting scheme with this address map provides a total of 64 subnets. Take the time to understand the other examples before proceeding. The formula for the total number of addresses per subnet is 2 to the h. The formula for the total number of usable addresses is 2 to the h minus 2. The h represents the number of host bits in the address map. Recall that we subtract 2 in the total usable formula, because neither the network address nor the broadcast address can be assigned to a device. The address map in the first entry shows 19 host bits. Uppercase letters represent 8 bits. 2 raised to the 19th power gives the total number of addresses per subnet. We can then subtract 2 to obtain the total number of usable addresses per subnet. Review the other examples before proceeding. Next, we will use the subnet address map to determine the subnet mask. In this case, set the network bits to 1 and set the host bits to 0. Let's consider the first entry. It corresponds to a Class A address because it has 1 uppercase N, or 1 classful octet, representing 8 network bits. Next, it has 5 subnet bits. And as we've been saying throughout the series, subnet bits are network bits. To get the corresponding subnet mask, set the network bits to 1. Then set the host bits to 0. This provides a subnet mask of 255.248.0.0. In the fourth entry, set the 26 network bits to 1 and the 6 host bits to 0. This provides a subnet mask of 255.255.255.192. Feel free to examine the other examples. We could also use the subnet address map to determine the wildcard mask. There are other ways, but we will focus on this method for now. The wildcard mask is the inverse of the subnet mask. Set the network bits to 0 and set the host bits to 1. Consider the third entry. To get the wildcard mask, set the 20 network bits to 0 and set the 12 host bits to 1. This provides a wildcard mask of 0.0.15.255. In the fourth entry, set the 26 network bits to 0 and set all 6 host bits to 1. This provides a wildcard mask of 0.0.0.63. Analyze the other examples before proceeding. What this series calls the interval, others may refer to it as the increment, magic number, or a variation of the term block size. When subnetting, the interval will help us determine subsequent network addresses. It will also help us analyze a host address. The interval can easily be extracted from the subnet address map. It is the place value of the rightmost subnet bit within the octet. When you consider each octet in isolation, there are only 8 possible values. Each value is a power of 2, so we will use the table shown here to help us in the process. In this example, the rightmost subnet bit is the third bit in the second octet. Let's look at only octet 2. Note, the place value of this bit within the second octet is 32. Thus, the interval is 32. In the second example, the interval is once again the place value of the rightmost bit within the octet. Consider octet 3 in isolation and focus on the rightmost subnet bit. It is the last bit in the far right. Thus, the interval is 1. In example 3, the last subnet bit from left to right is the fourth bit in the fourth octet. The place value of this bit within the octet is 16. This is the interval. Please review the other examples. Additional terminology we will use to analyze host addresses include the transition octet, the TOV, GTOV, and the NATOV. A brief description is provided here, but we will elaborate on each term. The transition octet can be derived by considering the subnet address map. It is the octet where the rightmost subnet bit resides. It's the same octet from which the interval is determined, and where the bits transition from subnet bits to host bits. Consider the first entry. The rightmost subnet bit is in octet 2, so this is the transition octet. In the third entry, the rightmost subnet bit is in octet 3, so octet 3 is the transition octet. In the last entry, the rightmost subnet bit is in octet 4, so octet 4 is the transition octet. The transition octet value, or TOV, is the numerical value specified in the transition octet. For example, in the second entry, octet 2 is the transition octet, and its value is 15. Therefore, the transition octet value is 15. In the fifth entry, octet 4 is the transition octet, and its value is 22. So the transition octet value equals 22. The given transition octet value, or GTOV, is the same as the transition octet value. The only difference is that it refers to the given host address to analyze. Whereas the TOV is generic, the GTOV refers to a specific address, the one given. In the first entry, octet 2 is the transition octet of the given host address to analyze. Its value is 44. This is the GTOV. In the third entry, octet 3 is the transition octet of the given host address to analyze. And its value is the GTOV. That would be 13. The network address transition octet value, or NATOV for short, is also the same as the TOV. The difference is that it refers to the TOV of a network address and not a host address. We will use it in a formula to help us determine the network address of a given host address. Before proceeding, let's briefly describe the trunc function. It shortens a number by removing or discarding the fractional part. It does not round up or down, it simply drops the digits to the right of the decimal point. Given a host address, we will use the trunc function to help determine the corresponding network address. Here are some examples of how the trunc function works. The answer is always an integer. We will use the NATOV formula to determine the network address of a given host address. We will take the GTOV of the given host address, divide it by the interval, truncate the answer, and multiply it by the interval. This will give us the NATOV. Given a host address, these are the steps to determine the corresponding network address. Step 1. Determine the subnet address map, the interval, the transition octet, and the GTOV. Step 2. Apply the NATOV formula to determine the NATOV. Step 3. Replace the GTOV with the NATOV. Step 4. Set all host bits to 0. However, if the transition octet is the fourth octet, we can skip this step. Let's look at an example. Given the address 192.168.1.99/26, determine the corresponding network address. We start by determining the address map, interval, transition octet, and the given transition octet value. First, the subnet address map. Since the first octet is 192, its native class is C, so it has 3 classful octets. Each one of these octets is represented using an uppercase N, as noted in the native address map. We then borrow 2 host bits and convert them to subnet bits to account for 26 network bits, as noted in the prefix length. Finally, add 6 host bits to account for 32 bits. The interval is the value of the rightmost subnet bit. 64 in this case. The transition octet is the octet where the rightmost subnet bit resides. The fourth octet. The GTOV is the numerical value in the transition octet of the given host address to analyze. In step 2, we apply the NATOV formula. Plug in the GTOV and the interval. Calculate the GTOV divided by the interval. That is, 99 divided by 64. This gives 1 dot something. When we truncate it, we simply get a 1. 1 times 64 is just 64. This is the NATOV, or network address transition octet value. In step 3, we replace the GTOV with the NATOV. When we do this, the 99 becomes 64. Step 4 is turning off the host bits as needed. This means setting them to 0. However, since the fourth octet is the transition octet, we can skip this step. And this is the network address 192.168.1.64/26. To get the first usable address, add 1 to the fourth octet of the network address. This gives 65 in octet 4. Here are additional examples of how to determine the first usable address. Before we determine the last usable, or assignable, address, it is typically easier to determine the broadcast address first. The broadcast address has all the host bits turned on, meaning set to 1. To get the broadcast address, we can add the wildcard mask to the network address. Looking at our specific example, add the network address and the corresponding wildcard mask. This gives a broadcast address of 192.168.1.127. To obtain the last usable address, we subtract 1 from octet 4 of the broadcast address. This gives 126 in the last octet. In example 2, once again, add the wildcard mask to the network address to get the broadcast. And subtract 1 from the broadcast to get the last usable. Here is example 3. Add the wildcard mask to the network address to get the broadcast. And subtract 1 from the broadcast to get the last usable. And example 4 for your review. Add the wildcard mask to the network address to get the broadcast. And subtract 1 from the broadcast to get the last usable. Finally, we provide 3 additional examples of finding the network address for a given host address. Study them carefully. In example 1, determine the address map first. Then use it to extract the interval and transition octet. Identify the GTOV from the given address. Apply the formula to get a NATOV of 192. Replace the GTOV with the NATOV. And finally, turn off the host bits. This gives the network address of 10.192.0.0/11. In example 2, first determine the address map. Then use it to extract the interval and transition octet. Identify the GTOV from the given address. Apply the formula to get a NATOV of 128. Replace the GTOV with the NATOV. And turn off the host bits. The network address is 172.16.128.0/18. Use the same process for example 3. Determine the address map, and then use it to extract the interval and transition octet. Identify the GTOV from the given address. Apply the formula to get a NATOV of 48. Replace the GTOV with the NATOV. Since the transition octet is octet 4, we are done. The network address is 192.168.1.48/20. That's it for now. Thanks for watching. And remember, nothing worthwhile comes easy. So go forth and subnet a little bit.